Okay, let's start the scientific part of the conference. The first session is experiments with laser-cooled atoms. And for this scientific part, each invited speaker has 20 minutes for their talk, and we have 5 minutes of question and discussion time. Yes. So the first invited speaker is Professor Arno Rauschenbeutel from Humboldt University of Berlin. And the title of his talk is Hybrid Trapping of Cold Atoms with Surface Forces and Blue-Detuned Evanescent Light on the Nanophotonic Waveguide. Listen, please.
Okay, thank you very much, Takao, for the introduction, and also thank you very much for the kind invitation. It's a great pleasure and honor for me to present our results to this distinguished audience. And actually, yesterday evening after dinner, I learned that there may be like non-experts in the audience, and I panicked and then made some last-minute modifications that I hope also make it enjoyable to those that are not experts. So, and along these lines, I would like to start by introducing the main ingredients of that feature in the title of the conference. And you already said a few words about why we would like to interface photons and atoms. Photons are great carriers for transmitting information and also quantum information. And atoms are actually super well known quantum objects, very well controlled with lasers, and they are actually also nowadays used for defining the second and so on. But I would like to feature one particular thing, because also from an economical point of view, they are super cheap. So you get like 1,000 billion atoms for $1, you know? I mean, beat that. Okay, so all this makes it desirable to realize some quantum interface between atoms and propagating photons. And there, nanophotonics can help, because nanophotonics allows us to confine and guide light, which allows us to have some enhanced coupling to atoms near some guided mode and some nanophotonic structure. And it also allows us to interface not only one or a few, but many emitters, as Takao has shown in his impressive talk. And our platform for realizing such a nanophotonic interface are optical nanofibers. So optical nanofibers are cylindrical dielectric waveguides with a diameter smaller than the wavelength of the guided light. And in these waveguides, the light is not only confined to the inside, but a significant part of the optical power propagates outside of the waveguide in the form of an evanescent wave. So maybe evanescent wave is not familiar to you, but this is not just some theoretical concept, but you can actually really touch it, okay? So right in the next coffee break, take a glass and look from the top. And then you see when light is reflected from such an interface between the glass here and the air outside, then if you touch the glass, you see your fingerprints. This is actually the same method that you use at the airport for detecting or recording the fingerprints of people. And this is because the light is not actually confined to inside the glass when it's reflected. It sticks out a tiny bit beyond the glass, and you can touch that, okay? And then you scatter that light, and it's missing, and you see your fingerprint. So, and if we now couple atoms to this evanescent wave around a nanofiber, then this is pretty efficient coupling. So we can actually have absorption of 8% per atom, okay, so almost 10%. It doesn't seem to sound like a lot, but compared to free space, this is already a good, I mean, like free space focused beams, this is already a good number. And then it's also actually possible to have many atoms coupled, and then you get really very highly efficient nanofiber-based atom light interfaces. So the nanofiber is realized, as Takao showed, in the form of the waste of a tapered optical fiber. And the nice thing is that if you now launch light through this fiber, you can have sub% losses or even sub/mil losses, as Takao showed. And we have this pronounced evanescent field. And if we now trap atoms, and we can trap, say, a few thousand cesium atoms inside that field with a coupling strength of a few percent, then this puts us into a regime for the experts which singles us out from other like matter-light interfaces between quantum dots, molecules, or superconducting qubits, because while our coupling is not so strong per emitter, we can have many emitters and are in this corner here, okay? So I say when we trap atoms, the question is how can we do that? And we actually achieve that by launching far detuned light fields to the fiber, two of them. One is red detuned and the other one is blue detuned. Now you may wonder why a detuned light field inside such a fiber allows you to trap atoms around it, but this is actually the so-called dipolar force, and again this is something you can see in everyday life. If you take some plastic stick and you rub it with a cloth and then approach it to polystyrene flakes that you have from your Amazon delivery, then they will stick to this like charged plastic, because the charges here induce dipole moments in the polystyrene, and then this dipole feels a force towards the stick. And the same thing happens with atoms when you have red detuned light in the fiber. But the beauty is that if you increase the frequency of the light, I mean, here it's like DC charges, right? But if you work with oscillating electric fields, then you can go to a regime where the frequency is higher than that of the atom. And then this field does the opposite. So you can either attract or repel atoms from the fiber. And if you now launch both colors through the fiber, then you have both attraction and repulsion. And here I show the energy that is seen by an atom when it approaches the fiber from a distance. And since the red light has a longer wavelength, it sticks into free space further than the blue light. So the atom will first see some attractive red potential, and then when it gets closer, the blue repulsive potential takes over, and the overall trapping then can have, or trapping potential can have a minimum at about 200, 300 nanometers from the nanofiber surface, okay? And now, in addition, when you look closely here, our atom will feel some like very strong attractive force when it gets close to the fiber. These are the so-called surface forces, okay? So the surface force is a very short range but very strong attractive force, which will always win over the light-induced forces. And the surface force is, in our case, composed of two parts. So we have the surface force consisting of the Casimir-Polder potential and the potential due to charges on the fiber. And again, you may not have heard about Casimir-Polder, but actually when you use a Band-Aid, then at a molecular level, why this sticks on your skin is because of Casimir-Polder. So very useful force, okay? And again, the electrostatic charges will attract the atoms with a different dependence on the distance from the fiber, which is exactly the one from our charged plastic stick that attracts polystyrene beads. And now the question that we asked ourselves is, can we actually trap atoms using only the attractive force from surface forces and replace the red light by surface forces, okay? You can actually put the numbers, and what you find is that while using the right powers and detunings of the red and blue beam in the standard two-color nanophotonic trap, we have this trapping at 200, 300 nanometers from the fiber surface, and a depth here which corresponds to a temperature of 22 microkelvin for this specific trap. When you replace the red light only by the surface forces, then you would expect to trap the atoms more at 650 nanometer from the fiber, and the depth here is on the order of a microkelvin, and that is a problem. Because actually, we have very sophisticated methods of laser cooling atoms, and they get you to unbelievably low temperatures of, say, 5 microkelvin in our case, but this is still 5 times too hot for this trap to be loaded directly from these atoms, okay? And amazingly, and due to some accident, actually, we noticed that we can actually load this trap. I can tell you in the coffee break about the accident, but the story is that when we load this standard trap, we can detect the atoms by launching resonant light through the fiber, and we see the absorption from the atoms. And then when we look at that absorption over time, it decreases because we lose the atoms over some 50, 80 milliseconds of time. So this is the standard trap. We load atoms and then we lose them over time. And now what we did was to momentarily switch off the red laser field, okay? So then we are in this situation here. And when we switched off the laser field and switched it on again, the atoms were back in our standard trap. So we didn't lose them. We switch off the attractive force, we switch it on again, and we don't lose the atoms. So it seems that the atoms are actually somehow transferred from this very deep and near to the fiber trap to this very shallow trap here. And the reason that this works is so-called adiabatic cooling. So the trick is that if you have a potential which traps a particle, it doesn't have to be an atom, but just some particle in the potential, and let's look at the quantized motion and quantized energy levels, and let's suppose we are in the ground state. If you then gently change the shape of the potential, you will stay in this ground state, which means that if you then transform this deep potential to a shallow potential slowly enough, then you're actually very cold because you're still trapped in the ground state of this shallow potential. And the condition for that to work is that the change of the trap frequency is small enough, the change of the trap frequency in one oscillation period. And if we plug in the number, then it tells us that we can go from this deep trap here to this shallow trap here if we go much more slowly than 100 microseconds. So a millisecond should do the job. And indeed, if we look, so here is the power as a function of time of our red laser. So here you see that we switch off the laser in about a millisecond and then switch it on again in a millisecond. And if we now look at the efficiency of transfer from this trap to this trap and back as a function of this time constant here of the switching off and switching on of the attractive red laser field, then as a function of this time constant, we see that the loading efficiency goes up to about 80%. So we can transfer 80% of the atoms from this deep trap to this trap and back just by gently switching on the red laser. Now you would think that this, let's call it hybrid trap, because it uses two different mechanical, physical mechanisms to trap the atoms. This hybrid trap should actually have a much shorter lifetime. It must be a horrible trap, right? Because it's super shallow, microkelvin deep. And as Takao showed you, as I showed you in our standard trap, we usually manage to hold the atoms in this trap for some 50 to, say, 80 milliseconds in our case. And we would certainly expect to have a shorter lifetime in our hybrid trap. But it turns out that no. If we look at the number of atoms, and this is a log plot here, like semi-log plot, then we see that the atoms stay longer in our hybrid trap than in our standard trap. Actually, the lifetime of the atoms in the trap is almost twice in the hybrid trap, which is so shallow, than in the standard trap. And this is actually a very intriguing result. So because it turns out that what really limits the lifetime in such nanophotonic traps or nanofiber-based traps and nanophotonic traps is an open research question. Nobody really knows, okay? And it also turns out that it's very rare to find some knob that increases the lifetime. It's very easy to spoil it, but to keep atoms for longer is very hard. And still here, in this hybrid trap, we do see an increase of lifetime in spite of the shallow trap here. And then we ask ourselves, okay, so if it's better for the lifetime, what about coherence time? So again, for the non-experts, cesium is the atom that defines the second, and it does so by the frequency of the so-called hyperfine transition between the two ground states of cesium here at 9.2 gigahertz. And this is also a system here, these two hyperfine ground states, which is very useful for quantum information processing. So the time that a coherence, a quantum mechanical superposition between these two levels lives is actually a crucial quantity. And it turns out that in our standard trap, we have measured this coherence time, and we find about a millisecond, which is due to so-called, for the experts, differential light shifts between the two levels here in conjunction with the motion in this trap. Meaning that if we look at the Ramsey signal here for the experts, we see that coherence decays on the time scale of a millisecond, okay? And now what about the hybrid trap? It turns out that we win more than an order of magnitude in coherence time with the atoms stored in this shallow hybrid trap using only surface forces and the blue laser field. So also here, if we look at the Ramsey coherence as a function of the red power, so while moving the atoms gently from the standard trap and stop in between and look what is the coherence time there, we see that like the largest coherence time is found when the red laser is off, okay? And we are in our hybrid trap and we have about 16 milliseconds of trapping, of coherence time. Okay, now we would really like to understand what is the real nature of this surface force here, because I said there are at least two contributions and the relative strength we don't know. So, but there's actually a way to reconstruct this potential, because we know the blue potential here, which comes from the light field, very well. This is understood. We know the intensity distribution, the detuning, and so we can compute that. So if we now switch off the red light field and look, or if we turn it down and look at the position of the atom, okay, by measuring its absorption or coupling to the light field in the fiber, then this allows us to reconstruct the position. So we measure absorption of the atoms, assuming that it's the same number of atoms, it's just further away from the fiber, and then infer where are the atoms in view of that absorption. That allows us to then determine the average distance of the atoms from the nanofiber. And when we do this, then we see, I mean, this is the experimental data here, the blue dots, that we cannot explain this distance dependence or the power dependence of the distance just with the Casimir-Polder potential. If we only assume Casimir-Polder, then we would have this orange behavior here, this orange dashed line. If there were no surface forces at all, then this would what we would get. So both don't fit. And we actually have to assume that we have Casimir-Polder plus electric charges on the fiber, okay? And if we do that, then this fits well, and from this fit of our model, we can then also infer the number of charges per length of the nanofiber. And we find about 20 elementary charges per micrometer on the nanofiber, which is consistent with what has been measured, for example, using ions near dielectrics and ion traps. So it seems to make sense, okay? So with this, I would like to summarize. So I showed you that we now have a new kid on the block regarding trapping of and interfacing of cold neutral atoms, which is our hybrid nanophotonic trap. It is loaded adiabatically from a standard trap by gently turning off the red laser. Surprisingly, we have both a longer lifetime and, I mean, a longer, much longer coherence time here. So this is both good, and we could maybe use this trap for storing quantum information. So you could have the atoms close to the fiber, write some information into the atoms, and then move them away from the fiber where they are well protected, and then move them back again if you want to interact with them. But I would like to stress that the origin of the mechanism that leads to the trapping, so the origin of these surface forces, is still under investigation. So this is a great time for us because we stumbled on that, but we really don't know what it is, so we will have fun. But currently we are in about that state, okay? So we really don't know what is going on. But I should stress it's a very reproducible, stable trap. It has been operating for 9 months now without changing of trap parameters, which is a surprise because you would say, why doesn't the charging of the fiber change over time? The charge status of the fiber, if it is charges, seems to be completely constant. So with this, I would like to thank the people that really did the work. I thank the funding agencies, and I thank you for your attention.
Thank you, Arno, for a wonderful talk. So, Christian?
So thank you
what is the first motivation for turning off the red? So then I move the coffee break discussion to now. Actually, turning off the red is the standard way for us to check that we really trap the atoms. So because you load from a cloud of cold atoms around the fiber, and they may just, this cloud may still be around, and what we see when we observe absorption of atoms through the nanofiber guided mode might just be atoms that are still around. Cold atoms from a cloud that fall through this potential. And to rule out this possibility, our standard sanity check is to turn off the red light brutally, turn it on again, and if the atoms are gone, they were trapped. If we still see atoms, then there's still some rain of cold atoms falling along the fiber, and we don't trap atoms. And we had to realign an experiment after some incidents, and the postdoc then said, like after a week, oh, I have atoms back. But then he said, like, shit, I don't trap atoms. You know, I turn it off, I turn it on, atoms are still there, they are untrapped, okay? This is just background. And he kept on doing that for more than a month until he noticed that actually while he was realigning the experiment, he changed the driver for turning off the red laser, and this new driver was slower. So it's a complete anti-Murphy instance here, right? We knew that this trap is there. We thought about it many years ago, but we said no way that we can load this trap. It's too shallow, okay? And then by accident, turning off the red too slow to kick the atoms out of the trap, okay? We found this trap. So no motivation, anti-Murphy instance. But I should say, again, we knew that this trap should be there. We knew round about the depth that you would expect, and we just said, forget about it. It will never work. Yeah.
Any other question?
Out of curiosity, how did you perform the Ramsey measurement, and what is the limitation on your coherence time? What is the bottleneck?
Yeah. So, I mean, we perform the Ramsey measurement by having a microwave horn. We have a microwave horn nearby, and we irradiate the atoms with microwave radiation at 9.2 gigahertz. We start in one of the hyperfine ground states using optical pumping, so they are well initialized, and then we do a so-called pi half pulse, wait, another pi half pulse. And then we, as a function of waiting time, we see these Ramsey fringes. And now what limits it here in the standard trap is that the trapping light fields, so these far-detuned light fields, actually shift the ground state. This is how the atom is trapped. It shifts it down. But it turns out that it shifts the upper hyperfine ground state down a bit more than the lower one because it is less detuned from the red laser, for example. And now this shift is intensity dependent. That means if the atoms move in the trap, then depending on where they are, their transition frequency changes. And this motion-induced dephasing causes this decay here of the Ramsey signal, okay? This is called differential light shift, and then in conjunction with the temperature of the atoms, this causes the coherence to decay. And then if you think about it, it's not so surprising that here we have much longer coherence time, because in this trap, the atom is trapped at a place where there's essentially no light. The red is off, and the blue light decays with a decay length of less than 150 nanometers. So if you're 650 nanometers away, then the blue light is also very weak, meaning that these differential light shifts caused by the trapping light are much, much lower, and thereby the motion of the atom doesn't lead to the same level of dephasing. No. Yes.
You said we don't understand the origin. You said we don't understand the origin of the trap, but what could it be? And maybe as a question to you both of you.
Yeah, so, I mean, what could it be? The standard answer, as I said, would be we know that a molecule or an atom will be attracted by a surface because of the van der Waals force, or here we also, I mean, some people call it van der Waals, some people call it Casimir-Polder also for the parameter regime where we are. This comes from quantum fluctuations. You can imagine that the molecule is surrounded by a cloud of electrons which are wobbling around because they are quantum, and that causes some flicker of the electric field, which causes an attraction of the molecule to the surface. Okay, so this is one thing. But if we now make a stupid and simple model of Casimir Polder, then this is not strong enough. The attraction from Casimir Polder would not be strong enough. That doesn't rule it out completely, because one should keep in mind that we made a stupid model of Casimir Polder, and you can do more elaborate ones where you take the temperature of the fiber into account and possible Mie resonances in the glass. And we should also keep in mind that our glass fiber is not a glass fiber. It is in a whatever atom, in our case, rubidium atmosphere. So there is, cesium atmosphere. So there is cesium on the surface, even if it's only a tiny bit, because it's a hot fiber. So for the moment, we think that it's not Casimir Polder, but we would have to look more carefully in order to really rule it out in the realistic experimental situation, taking full account of the geometry of the nanofiber and of the composition of the nanofiber in terms of additional cesium on the surface and also water in the glass, because we pull our fibers using hydrogen-oxygen flames, so this is hot water vapor in the end that you use for heating the fiber that puts OH groups into the glass, which may have resonances. So we don't really know about Casimir Polder. And then about the charges, you would expect that some dielectric in a vacuum always charges up. So this is there will always be some parasitic charges, but where exactly they come from? So is it the blue light that has some photoelectric effects that makes electrons fly away from the fiber? Is it the cesium on the surface that is polarized because it loses a bit its electron into the glass and we get dipoles rather than monopoles on the fiber? We don't know. So we are now planning to do a whole series of experiments and sanity checks to find out. But the fact is, whatever it is, it doesn't change over time. Completely stable.
Okay. We need to move on to the next speaker. So let's thank Arno again.
Thank you.
Takao, can I take your USB-C? Oh, there is one. There is one here, Takao.
Okay. Next speaker is Professor Julien Laurat from Sorbonne University. And his title is Quantum Optics with Cold Atoms Trapped Along Nanowaveguides.
Okay, so good morning, everyone. Thank you very much for inviting me. It's a great pleasure to be in this meeting and to meet again many colleagues from Japan. So I'm Julien Laurat. I'm professor of physics at Sorbonne University in Paris. I'm leading a research group in quantum optics and quantum information networks there. We are developing different activities in my group, but I will focus today on similar devices we heard since this morning, how we can combine cold atoms and nanoscale waveguides. So I will discuss nanofibers, but I will go also to other generation of waveguide, which can include some structuration of the waveguide at the nanoscale. So this is a brief overview of my group. I won't enter into the details. We are developing various capabilities for quantum technologies, from quantum state engineering, how you distribute entanglement in a network, and which kind of entanglement you distribute. We are developing also quantum memory for light based on free space atomic ensembles, where we can reach now close to unity storage and retrieval efficiencies in this kind of devices. And the last activity of my group, which is basically half of my group, is how we can combine indeed atoms close to nanoscale waveguide, so trying to realize some all-fibered platforms. So this is what I would like to address today. So first, why we would like to do that. We heard already about that today. I will come back to the motivation and to the applications, and how we can combine, in which kind of devices, we have seen the nanofiber already, which kind of devices we can use to make this combination possible. So in the general field of research, of AMO research, a central goal is indeed to control the interaction between a single atom and single photon. And we have seen over the last decade many tremendous progresses. It can be, for instance, as I said before, quantum memories with very large ensemble of cold atoms. It can be all the work with quantum processing with atoms in high finesse cavities, and all the work we know about quantum simulation with also quantum processor units, which are now fabricated by some startup companies involving atoms in lattices and Rydberg arrays. So if the field is so successful in free space, I would say why we should bother with nanophotonics in the field. So here you have a few pictures, many of them coming from Arno actually, where you have atoms in the evanescent field of structure at the nanoscale, so at the wavelength scale. And then you can trap atoms, as you can see here, you can trap atoms in the vicinity. And then you will interact with the evanescent mode, with the evanescent field that Arno was introducing before. So first of all, it provides you some improved figure of merits. You can really confine the light thanks to this nanophotonic regime at the nanoscale. You can increase the photon energy density in this way. And it's also, if we think about quantum technology, it's a potential route for integration. It also provides you other degrees of freedom, which are other tools, other knobs you can play with. So when you work at the nanoscale, for instance, polarization has a kind of weird behavior. You will have a longitudinal polarization, and then it's not the polarization you are used to, and that can give you some chiral optics possibilities, like the light can decay in both directions in a waveguide, but they can also decay depending on the polarization in only one direction. So you can play also with this degree of freedom. So there has been a lot of effort. This is also why we are here today in the field, to combine AMO physics with nanophotonics. In my group, we have pushed also nanofiber for quite a long time, and we realized various experiments. So I will come back, I will show you a few experiments from quantum memories to a single photon router in a network. In the case of a nanofiber, as we have seen, we can trap many atoms, so a few thousand of atoms close to the surface, but the coupling is still limited. It's very nice relative to free space, but we can reach a few % coupling per atom. We can play with the number of atoms. We can play with the distance between the atoms, so many collective effects which can be studied and explored, and I will come back to that. But at the nanoscale, there are other ingredients we can play with. So here you have a picture of a chameleon coming from a scientific paper, actually, from colleagues in biology, trying to understand in Madagascar the color of the skin, which is not only related to pigments on the surface of the skin, but also on the structuration of the surface. So typically what you see here are, so here at the surface of the skin, you see some small change in the surface, some road at the surface. And the first one is a relaxed chameleon. This is the caption of the paper. And this one is an excited chameleon. And you see the color is changing, and actually it's correlated also to the spacing you have on the skin between these roads. So really at the nanoscale, it offers you another degrees of freedom, which is the control of the dispersion and the model property of the devices. And this is another degree of freedom we can play with. So that has been done in AMO, for instance, some seminal work by Michel Lukin, where he realized some nano cavities using photonic crystal waveguides. So here you have a waveguide with holes, and then you change the size of the hole, you will make a defect in this structure, and that will define a cavity mode. And then you can have a very strong coupling in this system. So that's one possibility. The other possibility is what we call slow light guiding. So that was pushed forward. Here you see the slow light race is on by Ben Engleton almost 15 years ago, which is if you propagate in this kind of devices, light, you can also slow down the light. So the light can propagate at a speed, at a group velocity, which is reduced relative to free space. So then you can increase the interaction by this slow light guiding. And that has been used in photonics. It's a way to increase, to reduce, for instance, the threshold of a laser or an optical parametric amplifier, which can be obtained here with a very small footprint. So one of the goals of my group is also to combine this engineering of the dispersion now with cold atoms. So this is typically the structure we would like to realize, you see, with cold atoms in the vicinity of a waveguide. So if you don't consider this part of the waveguide, typically you have a nanobeam, you have like a nanofiber, and we are adding this structuration on the side. And this structuration can introduce what we call you have here a dispersion relationship, a photonic band gap. So a gap in frequency, a range of frequency where the light cannot propagate. And then there are two effects which are very interesting. First of all, close to the band gap, so close to the band edge, the light is going to propagate very slowly. So for one atom, you will have a much larger coupling than what you get with a nanofiber. And we can reach a regime, this is the goal, where one atom will one photon will interact with one atom with a close to unity probability, and all that in single pass without any cavity. So that's one of the regimes, and it opens many possibilities in terms of quantum state engineering. You can think about a gate and make some deterministic state preparation, non-Gaussian state preparation, for instance. The second regime is if you enter into the band gap. If you enter into the band gap, so as I said, the light cannot propagate. But if you excite an atom, it will de-excite in a mode which is going to be limited in the range of space it can reach. So you have this decay, which is going to be tunable if you are more or less inside the band gap of the device. So it means you are creating what we call an atom-photon band state, which is tunable in distance, and that opens the path of some tunable atom-atom interaction in this system. And if you add many tools of atomic physics, Raman transition, B-field engineering in your system, then you can engineer a variety of Hamiltonian in this system with a tunability that you don't have in other potential systems. So we are very far from that, very, very far. It will take years to do that. It's very difficult, but this is a goal we would like to pursue. So let me go now to the lab. I would like to show you our two experiments in this direction. So the first one is an optical nanofiber you have seen. So you had a nice introduction before. So it will help me to go faster on this part and go to some applications. And then how we are developing now this new platform combining nanophotonics and atoms in photonic crystal waveguides. So in optical nanofiber, as you have seen before, we can trap thousands of atoms, which are going to be close to the surface, and we can address the atom directly with the fiber mode. So what we did in the past, the first experiment we did quite 10 years ago was an optical memory. So trying to have a photon, which is impinging in the fiber. You can stop the light, you transfer the excitation to the atoms, and then later on demand, you can read out the excitation. So the efficiency was still limited at that time. It was something like 10%. The atoms were not trapped around the fiber. And we are pushing now back this capability to reach much better efficiency on this all-fiber platform. Another direction is we can make, let's say I will say it this way, a single photon gun in this system. So that's, I will come back to that. So just to show you the nanofiber, but you have seen before, we trap the atoms. You have a SEM image here of a nanofiber. We trap atom in the vicinity, and we are using the way that Arno introduced, which is a two-color trap, blue-detuned light and red-detuned light, which are co-propagating in the fiber, which make a trap We have a few thousand of atoms at 200 nanometers from the surface. So how to make a single photon source with this system? We used what we call the DLCZ protocol, Duhan-Lucking-Sirac-Zoller protocol, which consists in preparing all the atoms in one of the ground states, and then you can prepare in a heralded way. So you know when you do it. You have a first detection event that tell you did create this excitation. So one atom is going to be excited among the thousands of atoms you are using, but you don't know which one is excited. So that's a giant quantum superposition of 1,000 terms, which are these atoms. So in this way, here is the schematics of that. So again, all the atoms along the fiber. You have a right field, which is going to induce some spontaneous Raman scattering into the fiber mode. I will detect in the fiber mode, at the output of the fiber, I just plug the fiber after a bit of filtering into a single photon counter. I will detect a photon, which tell me you have an excitation stored in your ensemble. And then I can keep it, not for long, for a few microseconds here, the excitation. But when I want, during these few microseconds, I can just send another beam, which is a read beam here, and emit a single photon directly into the system. So this is something which is done in free space. We were able to do it in this nanofiber configuration a few years ago. And the brightness of the source was pretty good, actually. If you trigger this read beam, we had a 25% probability to get a photon into the fiber. But there is another degree of freedom. So the two experiments I was discussing so far, optical memory and this single photon source, the array is non-commensurate in the sense the distance between the atoms is, for the atoms we are using, completely random. It's not random, it's periodically spaced, but there is no relationship between this distance and the atomic transition. So what we can do now is to play with the distance between the atoms. And we learn how to change this distance and go to almost lambda over 2, lambda being the optical transition for the atoms, lambda over 2 between the atoms. And then if you do that, so that was our paper in 2016, the first demonstration of a Bragg mirror in our system. Each of the atoms will behave as a small mirror, right? And then if you have exactly lambda over 2 between them, they are going to interfere constructively. So you do a Bragg mirror, as we know, for dielectric layers, for instance. But here you can do a mirror with 1,000 atoms. So that's what we did. We were tuning the distance between atoms, being very close to lambda over 2. We measured the reflection. I won't comment that. But we had up to 70% reflection for this Bragg mirror for a single photon. We can change the polarization, play with the chirality also of the waveguide, and get at the end some different spectrum depending on the probe polarization. We come back to this experiment recently, and we wanted to make now a control bidirectional router for a single photon. So there is two tools we are using basically. First of all is Bragg scattering. I can make my system a mirror if I control the order. So I send a photon or a qubit, it will be reflected. But I have another tool that I use usually for doing a quantum memory, which is EIT, electromagnetically induced transparency. So if I add in some over transition of the atoms that you see here, that was called a control field, you have a 3-level system. Then, in that case, I can make the medium transparent for the light, even if I have many atoms which usually absorb the light. So this is how we do a quantum memory. So what we did was to control in this system, to add a control on trying to get an input, single photon qubit, which can be either reflected or controlled. So a router which hopefully can be controlled at a very low power because everything is enhanced by the confinement of the light. So actually, if you do some transfer matrix formalism calculation, so very classical here, you can say you can find what is the spectrum in reflection of your system. So the previous experiment with no EIT control, my atoms are separated by lambda over 2. I get one band gap, which is a way to calculate here. You get one band gap. Yeah. And then now if you add the EIT control, you get a second band gap close to the 2-photon resonance. What does it mean in terms of... I have a problem with connection. So what does it mean in terms of spectrum? So here we plotted the reflection and transmission of the device as a function of the probe detuning. And there is a sweet spot. Again, this is something we can discuss during the coffee break, where this sweet spot is not at 0, but detuned from resonance. But there is a sweet spot where, if we have the control or not the control, we can really go to very efficient reflection and very efficient transmission. So this is typically what we did. We send a single photon, I mean a weak coherent state at the single photon level. And here you have the truth table without control. So you get the photon which is reflected and not transmitted. And then with the control, we can get the transmission and no reflection. So it gives you a directional router for the probe light. Then we characterize also the power needed to do that, and it was at the femtojoule level. So that gives you really a directional router which is operating at ultra low power due to this nanophotonic combination that we are using. In another experiment, we push even further the nonlinearity, down to a few tens of photons for this system. So this is the nanofiber. There are many exciting works to do working with this distance between the atoms. The second platform, as I said, is this photonic crystal waveguide, where now we are adding this control of the dispersion. So in this case, we need to design structures which can work with our rubidium atoms. We need to develop techniques to transport the atoms and explore novel protocols. So that's what we did. We developed first an open source package which enables you to calculate any trap in this kind of structure. So it gives you a versatile workflow for optimization. And we also had a few proposals of design that you can see here based on gallium indium phosphide. So we are working with C2N on Institut. You need a clean room to do that. In nanofiber, we do it ourselves in a clean environment, but we can do it with a flame and do it ourselves. For this kind of structure, we cannot, so it's a strong collaboration in Paris area. And this is the first waveguide that you can see here with a taper to couple the light. So two proposals, this one which is what we call a half W1, where we can trap the atom something like 100 nanometers from the surface. And we had even another proposal that we are studying. We also did the fabrication, you can see here, which is a comb waveguide, which is has different properties close to the bond edge, and we want to study how that will influence the light-matter interaction. You need to develop a new, that's what we did, a new cold atom experiment, also versatile, designed for that. So in our case, it's this is the experiment. Idris Dus, who is in the audience, is a leading PhD student on this experiment. So it's an experiment which is on a large alpha-meter translation stage. We can move the experiment, we can change later on the device from time to time. We can put it back with not too much alignment, hopefully. And we learned also how to trap the atoms. In the case of the nanofiber, as you have seen, very often we overlap the nanofiber with the magneto-optical trap, right? We don't need to have this motion of atoms. In this case, we absolutely don't want to overlap a large amount of atoms with the surface. It will change the dispersion properties. So we need to have these optical tweezers to move the atom. So we are here, what you see are single atom images. Each point is a single atom. We can do whatever shape with our special light modulator. And we are also developing very specific tools like higher order modes, tweezer trap, which are using some property of the varying phase of what we call the GUI phase in this setting, which should enable us to enhance our probability of loading atoms close to the surface. So this is challenging. We need to develop in all this combination we are discussing today, this fusion of nanophotonics and atomic physics is very promising for many applications. There are also a variety of tools we need to develop, and that we are benefiting a lot from all collaboration we can have in this direction. So let me thank my group and the sponsor of the work, in particular Alban Urvois, who is co-animating all my team, and Idris Dus, who is in the audience again, and will be very happy to discuss with you of all this experiment. So thank you very much.
So we can take just one quick question. Oh, if not, well, we can discuss after the after the session during the coffee break or lunch. So let's move on to the next speaker. Thank you. Let's thank Julien again.
Thank you.
The next speaker is Professor Sebastian Hofferberth from University of Bonn. And the title of his talk is Rydberg Quantum Optics with Ultra-Cold Ytterbium.
Yeah, thank you very much for the introduction and for inviting me here. Me and actually 2 members of my group, we are very happy to join this workshop today. I can very heavily build on all the 3 speakers before me who have introduced a large context and motivation for our work. Basically what we do in my group is very related to this in a variety of platforms, and we're always going for this theme introduced at the very beginning by Takao, looking for ways to interface quantum systems and building networks out of quantum systems. And ultimately, the carrier of this information in such a network will always be photons in our current understanding. And so we are looking for all kinds of ways to interface photons with whatever quantum platform we might use as a stationary node in such networks. And we also have work on fiber optics and the various ways of from waveguides to fiber cavities, but I have decided today to talk about a bit of complementary work, which goes a bit of a different direction than the previous talks. There will be actually no waveguides at all or fibers at all, but cold atoms and the same ideas. And if you have heard the previous speakers, what they have all stressed is what's usually challenging is to make photons, optical photons, interact strongly enough with single atoms. And that is true. So the solution for this in all the 3 previous talks is confine the photons and trap the photons in some nano optics devices to basically localize them better to interact with single atoms. And a kind of complementary approach we have been exploring, and many other groups are also exploring, is go to the other side of the story. Maybe do not torture your light so much, but leave that in free space. And instead use atomic properties to maybe trick this same challenge or solve this same challenge by actually changing the properties of the atoms to enhance the atom-light interaction. And the key to this is hiding in this word Rydberg, which you may have heard in the context of quantum technologies more often recently. So maybe just I will come back to this a bit more in the next 2 slides, what Rydberg atoms and Rydberg states are. To introduce this already, again, we are looking for ways to make photons interact strongly with atoms and then ultimately actually make photons strongly interact with each other and develop ways to control light at the single photon level, like we've just seen, build routers, build photon gates or switches and so on. And just to point out the difference here, many things are the same. We use the same ultra-cold atoms, we use the same lasers, but there is no waveguide. Our waveguide, if you want to, are 2 lenses focusing the light moderately to a few micron spot in free space. And in this focus of this most simplistic waveguide, where light still goes from one way to another to some detectors, in this most simplistic waveguide, we put in these ultra-cold atoms. And then again, we use all the technology you have already seen to move, position atoms. In our case, in this experiment, not on the level of single atoms, as you have also seen in these beautiful tweezers or nano fiber traps, but the similarly looking false color pictures in our case are not 1 atom, but actually some tens of thousands of atoms. So you cannot see this, they are not resolved, but instead of trapping single atoms, we trap whole ensembles of atoms. And that's very related to the quantum memories Julien was just talking about, and we are using many of the same schemes, EIT schemes, as he mentioned already, and collective excitation schemes than in this trick we are using. And finally, to bring in the other side, I promised the Rydberg states are just the states in atoms where we have excited the electron, not just a few quantum numbers as we usually do in experiments you have seen so far, but actually with the second laser then lift this excited electron to very high principal quantum number on the order of, for in our experiment, usually something like n equal 100. So we kick this valence electron even further away from the core, and this really, maybe we'll also come back later, we are making single atoms of the size actually larger than these nanofibers you have seen, significantly larger than the nanofiber. The electron wave function would cover this complete nanofiber and more, just because we excite the atoms to such high principal quantum numbers. And while this has many other interesting atomic physics consequences going to such highly excited states, the most important one in the context of this quantum applications is an idea that's now 25 years old, the so-called Rydberg blockade, using the same van der Waals forces that Arno just mentioned between atoms and fibers. If we take two such Rydberg atoms and bring them to this highly excited state, we have these van der Waals forces suddenly on distances of multiple microns, tens of microns, of significant strengths that we can measure and use this force in experiments. And in particular, this is shown in this conceptual graph for two atoms. If we have two atoms in the ground state, they completely ignore each other. Even if we excite one atom to the Rydberg state, they still completely ignore each other. But if we excite two atoms to the Rydberg state, then we see this strong van der Waals interaction if we move them closer. And we can turn this around. This is a beautiful idea of the blockade. If you actually already have atoms at a certain distance of each other, you can excite one of them, but you cannot excite the second with the same lasers because they are shifted out of resonance by the blockade. And this idea, combining this with these large ensembles of atoms, brings us to this Rydberg quantum optics, where we use this not just between two atoms, as is also now a hot topic in quantum simulation and computation, but in these large ensembles, where then one photon that is lifted to this, or one photon that is absorbed and then lifted to this Rydberg state, suddenly can blockade a whole large ensemble of atoms, thousands of atoms, and this is then felt by other photons. And this kind of mapping of interaction between two atoms onto two photons has turned into this field of Rydberg quantum optics, where we can do things that normally in free space or without cavities would have maybe believed to be impossible. We get this boost of interaction strength, and there's a large variety of demonstrated concept, very similar to what you've seen in the previous talk, single photon sources, single photon switching or routing, and also a bit more on the fundamental side, realizing this effective interaction between individual photons propagating through the medium with a huge flexibility and tunability of these interactions. And from our group, some contribution to this field is indeed showing such single photon switches and transistors in parallel to the Munich MPQ group, and maybe different, more recent example also from Paris and MPQ is to turn all these concepts really into actual photonic 2-qubit gates, where two photons are the carriers of quantum information, and via this effective interaction then you can realize the full gate. Here actually one has to admit it's a combination of this blockade effect and optical cavities, so these things are not exclusive to each other but can also be nicely combined as needed. And so now I'm done with my talk. No, I'm not. This is a bit a premature summary. I want to point out a little bit one direction we have been pursuing. If this all sounded very positive so far, yes, it has been for the last 10-ish years to do a variety of this proof of principle demonstrations, but far away, for example, for such a two-photon phase gate of in any way competitive or relevant fidelities. So now, of course, the question is, can we move on from demonstrating some nice proof of principle to actual application, or more towards application relevant levels of functionality? And if we look at the problems we face in these systems, like we have seen before, for example, in the nanofibers, it's a trapping, understanding the trapping precisely, and surface effect, and so on. the big challenge, or one challenge that comes in here for the Rydberg states is, as I mentioned already, and as you have seen also in Julien's talk, we use these kind of EIT schemes with 2 lasers to go to the Rydberg state. And the same effect that shows up in the quantum memories that decides the storage time in quantum memories is hidden a little bit in this phase factor. Here you create these nice large collective states on which also this single photon scheme is based. But this has to remain coherent for long enough for you to retrieve this information again. And what shows up here is the difference in wave vector or wavelengths of these lasers. And for the normal ground state scheme, this lambda scheme, this is irrelevant. You have almost no wavelength mismatch and everything is fine. But for these Rydberg states, by nature, by the 1/n squared scaling of atomic levels, this can be very unfavorable. And in particular, in the alkalis, which we all love to work with, this is hugely unfavorable. In rubidium in particular, this is a limiting factor, limiting the coherence times, for example, for these stored photons in gate operations to microseconds or below, even at these ultra-low temperatures. And then you can look for ways to overcome this, and there are only so many things you can, or there are multiple things you can do. You can, for example, try to combine this with structure trapping, as we've seen in the nanofiber. That's also one direction we pursue. But you can also look for nature being more favorable to you. Check your periodic table and look for a laser coolable element where this wavelength mismatch is by nature minimized. And it turns out this is a very not easy to find element in the bottom corner of the periodic table, ytterbium, where you have a wavelength of 399 and 395 nanometer, which is still not identical, but much, much better matched than for any other atomic species we could use for these experiments. And this minimizes this mismatch and then maximizes this wavelength or problem. On top, if you then check, you have a bunch of other, or you find a bunch of other advantages in particular, although this is a relatively complicated atom, heavy atom already, it actually turns out to be even more simple than the alkalis. You have 2 valence electrons, they add up to spin 0. You also have no hyperfine interaction in bosonic isotopes, so everything vanishes and you're actually back to almost a hydrogen-like level structure with a pure L0 to L1 to L0 transition, which is, well, also takes a lot of freedom away in optical pumping schemes, but also maximizes your efficiency and maybe makes this less prone to other problems you have. Then comes the question, well, can you laser cool these atoms and can you work with them? And it turns out, yes, there has been a large effort in recent years, actually also pioneered in Japan in the Kyoto group of Professor Takahashi for many decades. He has been a world-leading pioneer in ultra-cold ytterbium, and we have learned and copied a lot from there in building our own machine dedicated for these purposes, and can now, since a year or so, reliably laser cool and produce ultra-cold ytterbium atoms for these photonic or atom-photon experiments without going into too much detail here. If you're really interested in technical details, there are a lot in this more advanced laser cooling schemes, which we have also explored, but that's maybe not so relevant here. So we have these ytterbium atoms, and we can now start working on them as we do with rubidium atoms normally and look for this photon-photon interaction. Again, it sounds very good, everything, but life is never fully free, as you already know from all the other talks. I said ytterbium is a relatively simple element, that is true, but it's also a relatively heavy element where many of the simpler assumptions and things we know, for example, from rubidium and cesium fail, and you at some point at the precision we are interested in understanding these levels, atomic levels, really have to take multi-electron atomic physics seriously, and that is something we and others, in particular Jeff Thompson's group in the US, have realized and invested a lot of time in the last 2 years doing very old school atomic spectroscopy all of a sudden again. So you develop the most modern quantum technology, you then also have to do your homework and understand the basic atomic properties. And luckily for the Rydberg states, this is still relatively modest in complexity. Relatively modest in complexity. There is a method from the 1950s to 1980s, multi-channel quantum defect theory. But that also tells you a bit another maybe aspect of science. Things come in waves, and sometimes you rediscover things that have been 40 years forgotten, and they suddenly become very relevant again. So a lot of young people are now learning a multi-channel quantum defect theory again and advancing it forward so that we can get better and better understanding of these Ytterbium Rydberg states. And for those of you who don't want to learn this, I can point you to software by Jeff, which does a lot of the work, and I can point you to a software we have been maintaining for some years, which behind a nice GUI does all this complicated atomic physics for you, and now is also able to handle strontium and ytterbium and other 2 valence electron atoms. So if you really don't want to do this fun atomic physics, you can just rely, hopefully, on these packages. So that's one thing one has to learn. And then what I want to show you in the last 3 slides is a bit of experiments we have been doing in the last half year or so with this new system. Again, as always, you build a system, you have some ideas in mind, you want to do some science, and of course the beauty is there is other science to be done, and that maybe has to be done, but it also can be done. And what is interesting here is, I was mentioning before, we are going to this Rydberg states of incredible size, actually, at this 100 n equal 100 and beyond, blowing these Rydberg atoms up to some microns diameter. But we're also doing this in the bulk background gas, where we randomly position many atoms, as shown here by this green random atomic ensemble, and the red Rydberg atom we make, and the gray is supposed to be the blockade area. That's always the largest. That's nice. We can have no other Rydberg atom in this vicinity, but blue is a Rydberg wave function, which is also not negligible. So actually we can easily push in a regime where we make this Rydberg atom cover many, many other atoms. And you can ask yourself what happens in this regime. And this is a known regime also for some time. You actually suddenly start to do a very fun esoteric corner of chemistry. You have your atom that is not noticing all its neighbors. It's an ideal gas. But then you blow it up to some microns in diameter, and suddenly this electron can grab, at least with a tiny force, it can convey other ground state atoms, and at least temporarily in this ultra cold temperatures form some ultra long range molecules. We are making molecules of a ground state atom and a Rydberg atom of some few micron size. So these are incredibly unusual molecules. It's not Rydberg states of molecules. That also exists. You can take a real molecule and bring 1 electron to the Rydberg state. It's also large, but here really the 2 partners in the dimer are microns apart and weakly bound. And this has been something that has been investigated also in the alkalis with quite some detail by now in the last 10, 15 years in a kind of slightly different subcommunity of atomic physics. And we have now done these things for the first time in ytterbium. And these molecular states, you can think of it from a chemistry point of view, we photo-associate these molecules in the background gas. And basically how this shows up in our spectroscopy is there is always a atomic line here where we just make an isolated Rydberg atom. But if we find, by coincidence, a pair of atoms in the correct distance to each other to form such a bound ultra-long-range molecular state, we see additional peaks in a photo-association spectrum shifted by the binding energy. So what's missing in photonic energy here, photon energy we have to send in, is the binding energy in the molecule. And if you look at the scale, these are really binding energies on megahertz scale. So for chemistry purposes, this is incredibly low binding energy, but we can see them for some temporary time because they are surviving for some finite time in this ultra-cold atomic gases. And well, then, although we want to build photonic quantum gates, you suddenly talk to physical chemists, which also still exist and can do fantastic work, and you really throw on all the machinery of molecular physics and molecular binding. And we cannot do this anymore, but with the help of collaborators, Matt Iles and Milena Simic, who are experts on physical chemistry, we have been hard at work trying to really understand all the details of this physical chemistry. And you see here some examples of these molecular Born-Oppenheimer potentials that show up here. And again, I have to point out, if you have ever seen a Born-Oppenheimer potential, there are distances of the two cores in atomic units, normally Bohr radii, of 1 to 3. Here we are talking about a few thousand or thousand of Bohr radii distance between these two cores. And the Born-Oppenheimer potential turns out to be really determined by the Rydberg electron and its quantum mechanical wave function, its shape. So these wiggles in this Born-Oppenheimer potential are really the wiggles of the electron wave function, which you can see here. And if you want to see it a bit in a different way, by throwing in other ground state atoms into these into these wiggles of the wave function, you can really, if you want to, in some sense, map out this electron wave function, which the textbook, of course, thing we teach. This is how electrons behave bound to atoms, but which we can normally not see easily. And here, by seeing where these molecular peaks are forming in energy, we can then calculate back to where they are located in space, and we can really see how an atom samples this electron wave function. It's a kind of a very fundamental, interesting approach. When we go much more into detail, we can see all kinds of consequences of this atom-electron interaction. And just to show you a bit how physics can also look, if it's not yet polished into a gate or so, this is our current result of all the molecular peaks for all the quantum numbers we've measured. The black dots are the measurement, and all the colorful things are theory. And depending on where you sit from a physical chemist point of view, this is an amazing agreement between experiment and theory. From an atomic physics, you might say, oh, there's lots of points that are not so well matching, but here two communities have a bit of different view on what can be done. And skipping a lot of details here, maybe to come to an end, to briefly return you to the topic of this conference and what we are doing. We are also now starting, these are really first demonstrations of this Rydberg blockade in photon-mediated interaction in our Ethereum system from a few weeks ago. It's only now coming online. We see these EIT peaks, as we have heard before, some transparency window in the medium actually being suppressed by the Rydberg blockade, and that goes along with some photon anti-bunching we can measure in the output. That's a hallmark of seeing this interaction, and this is by far not yet at the level of what we can do in the rubidium systems, but this is our next step. And with this, I'm way over time, and I want to finish. Thank you.
Thank you, Sebastian, for a wonderful talk. So now it's open for a question. Yes, please.
Okay, very nice talk. Thank you very much. So there is this trilobite where you have the bonding between the Rydberg state and the ground state atom. Can we hope to try to have a bond, a nanofiber within the Rydberg orbitals at some point?
Yes, this is of course a very interesting question. We are also looking into in a separate experiment if we actually combine these nanofiber ideas with the Rydberg Rydberg excitation, what could happen. In the best case, you could think, okay, could the nanofiber really be a controlled object inside your Rydberg wave function? I would be a bit pessimistic based on what Arno has shown us before. The nanofiber is not a single atom. It's a highly complex charged, nano, but let's say from this perspective, maybe still macroscopic object, where, to say it is simply, probably all hell breaks loose. But this is something we would love to test.
Okay. Any other question? Okay. If not, let's thank Sebastian again. And the last speaker for this session is Professor Lucia Hackermueller from University of Nottingham. And her title is Bayesian Sensing and Photon Storage in Micromachined Waveguides.
Okay, thank you very much. Thanks for bringing me here. I think it's a wonderful conference, a wonderful combination of topics. I hope I will stay in time because I'm the last speaker of this session. So I am at the University of Nottingham, and together with my group we have some experiments on not nanofibers. I will show you the difference in a moment. So we have 3 topics for today. So we use cold atoms in intersected waveguides. I will also tell you about our Bayesian optimization for improved readout and sensing, and some elements, 3D printed elements for portable quantum technologies. So the first thing is our atom-photon interface, and we heard already a few approaches that work very, very nicely. So what we have understood is that combining atoms and photons is complicated because they are both small. So if we have an atom and we can put it in the center of the mode, we get a better connection between the two. The nanofibers, they live in the evanescent field. And this is our approach that we are using here. So we take an optical fiber. This is our picture of an optical fiber. And we drill a hole orthogonal to the fiber. And then we put our atoms into here. And that has some advantages and some disadvantages to the other systems that have been shown before. So one advantage, for example, with respect to Rydberg atoms is that you're further away from the surface and you're less prone to interactions with surface charges. In principle, we can also make several holes and then have several ensembles that can be connected with each other. And we can also transfer this to a chip situation. And then this links to what Julien has shown us so nicely. So this is how our fibers look like. So I told you we drill a hole. This is about 30 microns. We can do between 10 and 30 microns. We can shape them in this funny way. The reason is that a round hole, which was our first approach, is actually a bad idea because it gives you a dispersing wavefront, and this one gives you a focus. The green line is the fiber core where the photons actually travel. So our atoms will sit here, and this is another shape that we can make as a rectangular system with about 20 microns is the spacing here. So then we have to put the atoms in. We make them out of a magneto-optical trap and then load them into a double trap and intersect that with the hole. And this is how it looks like when our atoms pass through the fiber. So the red is the atoms and the blue is the optical fiber that you can see here. So this is about 100 microns. And then we have to do many experiments. So we load our trap and we probe and we load and we probe and we load and we probe. So blue is without the atoms, and red, all the light has been absorbed by the atoms in the fiber. And we get about 94% absorption, and we can trap between 300 and 500 atoms. But we have to be aware that this is a tiny volume of 500 cubic microns. And we can then, through the fiber, probe the absorption profile of our atoms. And this gives us an optical density between 3 and 5. And we can also use that to create slow light and photon storage. There is a poster on this by Alexander Abbey, and he will tell you all the details about it. So we again set up an EIT structure and get a nice EIT feature. Again, in this tiny ensemble of atoms, we get about an optical density of 5 and a delay time of 15 nanoseconds, but that can still be used in a small arrangement. So now I move away and I go to this adaptive Bayesian sensing. And so what is that? What we always want to do when we use a quantum sensor, well, we want to measure something as precisely as possible and as quickly as possible. So we have a system that we want to probe with a meter component, which is typically light. And then we probe our system indirectly, and we measure the number of photons on the detector. And now we have noise in both components here, in the meter and in the detector, and that is of course not great. But we know we can still get infinitely precise measurements if we take infinitely many measurements. So that is not convenient, right? We have to take many. It takes a long time. We can only get the finite precision. An alternative approach to that is to optimize, use Bayesian techniques to optimize how the measurement is done. So again, we have our atomic system, and that has a parameter theta that we want to probe, and we do that typically with some resonant frequency with a probe light, and we have some prior information about this. So the example that I will tell you about is we want to measure the atoms in our hole. That would mean our probe is the frequency that we send in, and our prior information is, well, it's larger than 0 and possibly less than 1 million, let's say. And so we send this through and we get an answer, which is we get a number of photons that have been absorbed for this specific frequency, and that means we have a prior probability of this photon number for theta under this control parameter yk, which is the frequency. So depending on the frequency, and now we can calculate the feedback mechanism. So we find out, we calculate a gain function. So this gives us some information about theta. And from that, we calculate a gain function that tells us how good was this frequency nu that we have used. And we feed it back into the system. Here's the feedback. And so we calculate a new frequency, and we take it again to probe the system, get another result, and go back and do this many, many times. So this is a general method that you can apply for sensing or state readout. What you need is a control parameter that can be used to optimize the sensing process. But actually, most measurements have some kind of control parameter, depend on something. So for example, what I will talk you through is to read out the atom number in high density samples. But you can also think of temperature measurement. That would be the timing in a typical time of flight that you optimize. It does not have to be regularly spaced. It can have different spacings. You can also, in an absorption profile, you don't have to take all the shots. There is a certain optimum of the number of frequencies that you want to probe. Or also in interferometry, you might want to choose on where you want to be on the slope of your interferometric fringes. So these are just examples. So to come back to our problem of atom counting, in these nanofiber systems, quite often we have a dense optical sample, which means we are here on the red curve, and the sample is flat with respect to the detuning. So we cannot immediately get back the atom number. So it's not clear what would be the optimal frequency to use to test the system. And therefore, here is a number of choices. We could be on resonance. We could say, well, it's probably not so good. Maybe let's be on the slope. So let's try to be detuned. Or let's use some optimization to find the best frequency beforehand, which would be to find an a priori Bayesian frequency, or to analyze, just take Bayesian statistics to analyze the on-resonance probe, or to vary the frequency as in our adaptive approach. So this is what we do, and this is, so we take always 30 measurement shots. Here are 3 repeats of these 30 shots. Each color is for one measurement sequence, and you can see how the frequency varies as we repeat our measurements and always adapt the knowledge that we have. And these are examples for the gain function, for example, after the first shot or after 4 shots and so on. So, and then we can compare all the techniques. So the on resonance, this would be the normal way how you probe your atoms, leads to this distribution. So that would be your measurement result. You can see detuned, although it seems reasonable to do that, is actually quite a bad idea. That gives a large variation. This is the reading out the blue data with a Bayesian system. And this is the a priori guessing, trying to guess the best optimum frequency. And this is what you get from this adaptive Bayesian approach. So you can see it's a much smaller variation. We get a better measurement result. So here we prepare the system always with 280 atoms as close as possible and analyze it with different methods and then repeat it 30 times. So this shows you again the width of the distributions that we have measured, and you can see the adaptive one is much narrower than the other methods, and we get an improvement. So this is the noise to signal ratio of our sensing is 0.2%, while for the standard method it would be 0.9%, and that's an improvement of a factor close to 5, 4.9. And we can also do that as we go along and increase the number of shots. So here we start with 1, 2, and 3, and so on, always analyze our result, and we can see that the adaptive method is always better than all the others. And if we go through all the 30 measurements, then we get this improvement from 0.2 to 0.9. That would be the standard way of doing it. So this is this factor 5, but we can also say, well, maybe we are happy with the precision that we get, we want to get that faster, so we would get the same precision as the standard method already after 9 shots, so just below 1/3 of the shots that we needed before. So we can either get an improvement of the signal by a factor 5, or we only need 30% of the data. So, and with that I get to my last part, which is to use 3D printing systems methods. So this is for portable quantum technologies. At some point we want to get these systems out of the lab and carry them around and do measurements. And we have seen that quite often these are complicated systems. So this is one setup that we have built that creates a cold cloud of atoms, 10 to the 8 rubidium atoms. Should come up somewhere. Here they are, a cold cloud of rubidium atoms. And this system is about this big and consists of a 3D printed, world's first 3D printed vacuum chamber, together with compact laser system and compact DFB lasers. So this is a picture of one of our other labs. This is how cold atom systems normally look. This part, what you can see here, is basically replaced by those lasers that are combined here. And this is a close-up of our 3D printed vacuum chamber. So the advantage of using 3D printing methods is that we have no limitation in the design that we want to implement. So what is 3D printed is this body that you can see here, and you can see this funny foam-like structure, and the reason for that is that you can remove material and still get optimum stability, and you can, even if you know that your system will suffer from some kind of stress because you, for example, send it to outer space, then you can create some reinforcements in the places needed. So we can create a UHV chamber without any design restraints, and the material that we have used here is ILC10Mg, which allows a weight reduction of 70%. I don't have one of these chambers here, but I could hold it in my hand and throw it like that, which I can't do with a stainless steel chamber. It has a weight of 245 grams, and we can reach below 10⁻⁻10 millibar in this. We have also printed titanium-64, which is quite desirable for some systems. And we have noticed in this system that the 3D printing is a funny, complicated process also that creates a rough surface structure. But interestingly, that does not limit the vacuum that we can get. So therefore, we thought, okay, let's make it more rough and see what happens. So we created these two structures and coated them with a kind of glue, so non-evaporative getter coating for vacuum pumping. You can also use that to shape the direction of a gas if you want. So these are the printed flanges. And then we apply this coating, and this can be a pump at the inside of your chamber and can also create stability. This is a close-up how it looks like. So this allows us to improve the pumping efficiency of a surface. I think this was our best one that created a 3 to 4 improvements in terms of, in comparison to a flat surface. And that means a CF40T piece of a volume of 0.17 liters, we can pump that to below 10⁻⁸ for 3 days without any additional pumping. So we take out the air, then we use our surface pump and keep it at this pressure for 3 days. We also looked at, this is one of the fun things that the 3D printing allows you, right? You can go to funny shapes. So this is an Escher pattern, Escher tiling, and for this we would actually get an increase in pump rate between 8 and 9. And a straightforward application of these systems are portable quantum technologies. So this is a layout for a gravimeter that is supposed to go to space at some point. So it's important that it's lightweight and compact. And we will also build an accelerometer that we will hopefully be able to move around. This is a short close-up on the lasers that I've shown you. So these are 3D printed mounts basically that allow you to shrink your optical table into something that is small and compact and robust and therefore much more reliable if you want to take it outside the lab. The last element that we have printed are vapor cells. So here you take glass particles together in a matrix, in a sort of plastic matrix, and they are printed, so you get your cell first looks like this, and then this undergoes a thermal treatment. It gets heated up to 1200 degrees, and then slowly heated down again, and then all the plastic evaporates, and you're left over with glass. And you can see here that we can pass laser light through, and these are the vapor cells that we can make. And so they have a transparency of more than 90%. And I'm not showing it to you, but the polarization stability is also comparable to normal glass. And again, the advantage is you can make structures that you cannot, cannot make easily, or you cannot make at all with the normal glass blowing approach. So here are two cells put together. You can also integrate gratings. You can functionalize the cell, so you can add some gold nanoparticles that create a surface plasmon that lead to specific absorption in the glass. And one can also print on a detector directly on the cell, which we have used to measure the temperature increase through the nanoglass nanoparticles. So this is a graphene detector that's interdigitated with silver, and that can be used to measure heat, but also to detect photons. And we have used these cells to measure spectroscopy. So you can see the printing leads to some kind of roughness, but this is the fluorescent beam, and one can clearly see it, and one can do Doppler-free spectroscopy. So, and also whenever we print these cells, we're getting better and better. So the blue line shows you the Doppler-free spectroscopy in the small cell, which is about 5 millimeter in diameter. The yellow one is a standard vapor cell, which is 7 centimeters. But if you calculate out the increase in optical path length, the glass cell, the printed glass cell does as well, or even a little bit better than the standard cell. And we can also use that to stabilize a laser to that cell. So this is the Ln deviation for the locked laser to the printed cell. We have tested them to pressures to below 2 × 10⁻⁹. That's probably limited by the highly specialized method that we're using here, which is gluing it on, and not by the glass. And the Ln deviation for the laser is 10⁻⁻10 delta F over F. And with that, thank you very much for your attention. I want to I'll tell you about my summaries. I told you our intersected waveguides, and hopefully convinced you about the usefulness of Bayesian sensing, and showed you 3D printed systems for portable technologies. And with that, I want to thank our funders and the people working on this. Alex is here and will present a poster. Nathan Cooper is a very experienced postdoc. Our theory collaborators are Janet Anders and Jesus Rubio, particularly in the Bayesian things. We have an open postdoc position. We also have a new quantum master course starting in 2026. And with that, I thank you for your attention.
Thank you, Lucia, for a wonderful talk. And now it's open for question. Yes.
Thanks for the talk. I was surprised to see that the structuring of your surface increases the pumping rate by that much, because, I mean, what is the difference in real surface area? I would think that if you have, say, active carbon, then one has these comparisons where you see it's a one gram gives you a football field of surface area. But here, in the end, you print something which has some structure, but it maybe doubles the surface, or is it more?
No, that is about right. So the surface area does not change as much as the pumping rate increases, and so we can do some nice Monte Carlo simulation on what we expect, because what you want to increase is the number of collisions with your surface. So the best thing, well, turns out this is why the Escher tiling works well. Narrow angles are good, because that gives you many collisions. So we have thought, but we have not implemented, also using fractals, which of course you cannot get to infinitely small, right? There's still a finite resolution, but that could be quite a fun thing to do. So narrow angles are good, and they lead to more collisions than what you just get from the surface, from the increase in surface area.
Any other question? Can I ask a question?
Yes, please.
About the micro machine fiber.
Yes.
So one could say it's more like a micro machine fiber coupler rather than a waveguide. I mean,
Yes.
you have two ends of the fiber which are coupled together with this hole.
Yes.
And so maybe I missed a point. So you showed us the round-shaped hole, and is it to increase the coupling efficiency between the two?
Yes.
And
Yes.
is it the cylindrical surface, not the round surface?
Yes.
They
So
yeah.
we also did some simulations on that a while ago. So as I said, we started with a round hole because it's the first thing that we tried. Also geometrically, that is challenging because the fiber, I mean, not for you because you do extreme things. The fiber is 100 microns and you take 30 microns out. But a round hole leads to a diverging beam, and the core is small. So the gap is huge for our photons. That's between 20 and 30 microns, and the core is just 5 microns. So we have to get them back into this core. And the cylindrical surface helps to shape to hit the core better, and therefore the coupling is better. Now, as you say correctly, it's a cylindrical, so not a 3D spherical surface. That would be even better. It's just that with our method, which is femtosecond laser drilling, we cannot do that at the moment. However, what we would like to study in the future is to make waveguides that are 3D printed, because then making the hole is easy. You do everything but not the hole. And you have a choice of controlling the refractive index in every point, which should be quite nice in order to control your light propagation. But yeah, so far we didn't have the chance to do that yet.
Thank you. Any other question? Okay. If not, let's thank Lucia again.